Sudipta from IIT Bombay, and he's going to tell us about sequential information theoretic protocols in continuous variable systems. Yeah, over to you.
So, thank you. Good afternoon. So, I am Sudipta, PhD student at IIT Bombay. I am working with Professor Himadrishekhar Dhar, and today I will going to discuss about the two sequential protocol in continuous variable system, continuous variable quantum communication. So, we know that in continuous variable quantum communication or in quantum communication protocols are use quantum mechanics for secure and efficient information transfer. They usually use quantum states, superposition, and entanglement. And entanglement is one of the key resource in continuous variable in quantum communication protocol. So suppose we have a two-mode state or bipartite state. So can we use this state in some communication protocol? So to use it, we need to check its entanglement. So it is entangled or not. So in that case, actually we address this question that can we check the entanglement of this state? So to do this, actually we verify this condition. So this is actually Duan inequality. I will tell you later what is this. And the second protocol is that if we use this two-mode states in some communication protocol, then if suddenly the communication protocol fails, then can we design a protocol such that we can reuse the state? So this is the two key questions, and we address these questions in our two protocols. So before I start with, so this is my actual outline. So first I will discuss about what is continuous variable quantum system, and then I will discuss about two protocols and then conclusions. So quantum information can be read in two ways. One is discrete variables and second one is continuous variable. So in discrete variables, information can be encoded in discrete levels. For example, qubit, qubit, or qubit. In continuous variable, we can encode information in continuous spectra like position and momentum quadrature. For example, coordinate state. So alpha is the we can encode information in alpha. So in discrete variables, usually if we perform projective measurement, the measurement outcome is a finite set. And in continuous variable, the measurement outcome will be continuous spectra if we perform homodyne or heterodyne measurement. So this is actually our continuous some introduction about CV systems. So first I will like to discuss about our first protocol. So suppose we have a two-mode system. So this is actually this entanglement criteria. So this two-mode will be entangled quadrature based relative quadrature based entanglement. So this is actually the necessary and sufficient condition for quantum teleportation and telecloning. So telecloning is a communication protocol which actually combines teleportation with optimal cloning. So so this is also known as Duan criteria. So we will detect this criteria within this some entangled state. So our aim is in that protocol is to determine for a given resource it is entangled or not, and if it is an entangled, then how many times we can detect in entanglement. This entanglement criteria is quite different from the bimodal entanglement like log neck or GGM type things. So to do this, we can perform projective measurement, but projective measurement usually destroy the resource. So we can know that the state is entangled or not, but we cannot use the resource in the next step or in further communication protocol. So that we will use the unserved measurement in that case. So this is actually protocol. So how can we implement this unserved measurement? Suppose we have two mode states. So SA and SB are our system resource, two mode system resource, and we will combine some auxiliary or meter state, single mode states with our two mode states locally and perform some unitary operation. So then we will measure the position quadrature of the unitary operation. So if we measure the position quadrature of unitary operation, we can know about the information about the position or momentum quadrature of the system resource. So for example, this actually depends on what types of unitary we are implementing. So for example, for the first mode, if we want to measure the position quadrature, then our Hamiltonian will be like this, and corresponding unitary will be like this. And if we want to measure the momentum quadrature, then here we will put the momentum operator of the resource. So there will be actually then 4 possibilities that we can measure the position quadrature of the both mode, or position momentum, or momentum position, or momentum. So based on this, we can get actually 4 probability distribution function, depends on what types of measurement or unitary sets we are taking. So using this probability distribution of the measurement outcome, these 2 outcome, we can calculate this non-classicality measure, or the Dhar criterion entanglement. So we can actually measure the non-classicality or the entanglement of this resource using the auxiliary system measurement. If we calculate the relative variance, quadrature variance of the auxiliary system, we can measure these things. So here we take an example. Suppose our resource is 2 more discrete vacuum state. So this is actually entangled state in very well in entangled state CV system. So if we take the 2 more discrete vacuum state, the quadrature measure, the non-classicality or the Dhar criterion will be like this. So here you can see that this is actually the actual entanglement of the 2 mode system, and this is actually the position quadrature variance of the auxiliary system or meter state. So if we set this to equal to 0, so if we set the squeezing of this meter state infinite, then we can directly perform the projective measurement and can read what is actually our actual entanglement of the 2 resources. So for finite squeezing, we can approximately measure these things. And after this measurement, the post measurement state can be written like this, just tracing out the meter state. So this is actually the protocol how we can detect the entanglement of the shared resource. Now the second thing is that how many times we can detect the entanglement. So for first step, we can actually perform these things, and there will be actually post measurement state. Again we can perform these things. So up to, I think we can take the up to n times we can do these things. So at the nth time, the total entanglement of the resource can be written as this. So this is actually momentum quadrature variance of the previous n-1 round, and this is actually the position quadrature variance of the last round. So we can take some restriction on these parameters, weakness parameters. So for example, we can take equal weakness parameters. So for entire process, for entire meter state, we can take equal position quadrature variance and equal momentum quadrature variance. So we denote as omega square, and the momentum quadrature variance is denoted as 1 by 4 omega square. So if we put these things in the expression, we can get how many times actually the number of detection. So now if we set the squeezing, if our squeezing of the resource, 2 more discrete vacuum resource is in this range, then we maximally we can get 2 times. But if we set squeezing at infinite, actually it will give 3. But if we take squeezing less than this quantity, then we will maximally get 1 times of detection of entanglement. Okay. And then the second constraint is that, so suppose we are taking the weakness parameters of the meter state same up to n-1 times, and the last one will be different. So this is the conditions. So for n-1 time, up to for n-1 times, our squeezing, our weakness parameters will be same, and the nth time will be is different. So if we plug this constant in this expression, there will be some mathematical things. So we can find some constant on the squeezing, then the weakness parameters. So for example, if we take, so this is just example, if we take our resource squeezing as 0.5 something, and the last weakness parameters as 0.5, and the up to n-1 times it is actually 1.08 something, then we can maximally detect the entanglement of this initial resource up to 8 times. So based on what types of, how many times we want to detect, we will change the parameters accordingly. So this is our first protocol to detect the entanglement and sequence, how many times we can detect its entanglement. It is related to that. The second protocol is that suppose we have some communication protocol. Usually we perform projective measurement to get maximum information transfer. So, but somehow we perform projective measurement and the protocol fails. For example, in teleportation and telecloning, there have a classical communication part. If somehow the classical communication part fails or forget to apply the unitary operation, can we retry these things, the teleportation or telecloning again? So we address this question in this setup. So to do this, actually there are a general protocol that suppose we have a 2 mode states, so we can split 2 mode states into 4 mode states using some vacuum state. So there will be actually then we can call this 2 as a transmitted mode and this 2 as a reflected mode. So in communication protocol, we can use this transmitted mode first, and we can preserve the reflected mode. In the next, if the protocol fails, we can use the reflected mode in next times. So we use these things in our teleportation protocol. So what we did, that we did not split the Bob part, but we just split the Alice part. So then the transmitted state can be written as the transmitted mode, these things, and the Bob part will be our transmitted state, and the reflected part will be these two. So now in these conditions, if we calculate the fidelity of the teleported state, these things, so this is actually a teleportation protocol. We will first combine a unknown state with this and then perform the projective measurement, and then Alice will classically communicate with Bob, and Bob will apply some unitary operation. So in that case, if we take the transmitted states as a resource, then the fidelity can be written like this. But if the protocol fails at the first step, and corresponding to, if we assume that it is fails at nth step, then the after nth time, the n-1 time, at the nth time, the fidelity can be written as like this. So in the next time, we will use the reflected part as a main resource, and then this fails again. So if we do these things several times up to n-1, then and if we perform at successful teleportation at nth time, the fidelity can be written as this. So in that formula, we also can impose some conditions on the transmissivity and the squeezing of the resource. So if we take the equal transmissivity, say tau, then these things we have plotted that we can maximally and retry this teleportation protocol up to 20 times. But if we set the equal fidelity, that we required minimum 0.51 or 0.505, 0.5 actually classical benchmark. So if we require the minimum fidelity, then we can see that the maximum teleportation reattempt number can be given as this. So they are actually an optimal squeezing where this will be maximum. So this actually comes from the shared non-classicality where the state will be maximum entangled. So this is our two protocol, and okay, and we can see that if we increase the equal fidelity, then the maximum number will decrease because it will take more entanglement of the resource. Okay. So in this protocol, we just show two protocols. One is again the entanglement detection, and another is the how many times we can reuse a resource in some communication protocol. And there have actually we find the trade-off between, in the case of continuous variable teleportation, we find the trade-off between the fidelity, resource splitting, initial squeezing, and etc. So this resource splitting protocol can be used any other protocol also. So thank you.
Okay, let's thank Sudipta again, and we have time for a couple of questions. Okay, let me ask one question. So, when you had this sequential process and you kept doing it over and over again, then what happened to the entanglement?
Entanglement will reduce every time.
It will keep reducing every time, right? So then there should be some, so then why is there this optimal number that you showed at the very end? Because if the entanglement keeps reducing, then one would expect.
In this case.
Yeah. So one would
usually it reduce, but there have some optimal setup where the entanglement of this I means that the process will be optimal. So at that time this is actually maximum. So if we see the non-classicality between these two mode, which I told earlier, Duan inequality. So at that case, the Duan inequality will be optimal.
I see. Okay. Okay, that answers my question. Okay, are there any further questions? Okay, if not, then let's thank Sudipta again, and let's also thank all the speakers of this session and the day.